So over to the next speaker, in that case, which is Carlos Contreras Pena. When he's plugged in, he's going to be talking about determination of outburst rate from 1 million years monitoring of planet-forming young-style objects.
Okay, so I'm here to talk about the work I've been doing at the University of Exeter with Tim Naylor, trying to determine the outburst rate from 1 million years of monitoring of planet-forming YSOs. We're trying to link the variability of young stellar objects with processes of planet formation. Now, planets form in these protoplanetary disks, and the crucial period for this formation is between 1 million years, when the first planetesimals have formed, and 10 million years when the protoplanetary disks around these young stars have dissipated. Now, if we think about these timelines and compare them to the different stages or phases of young stellar evolution, then this actually corresponds to this particular phase, which is the class 2 phase. Now, René has given a nice overview of the different stages of young stellar evolution. And this particular one, the class 2 phase, can be recognized in the spectral energy distribution because the near-infrared excess, because of this optically thick accretion disk, compared to the earlier stages where you have most of the emission in the infrared and the sub-millimeter wavelengths because the object is still deeply embedded. Now, if we think about planet formation, then the class 2 phase is the most important stage. Now, the properties of the disks then are important for the evolution and formation of these planets, especially surface density and the temperature, because these enter into the migration rates and also play a key role in the location of the snow line, which is used it's important for the chemical composition of planets. Now, these properties also depend on the accretion rate from the disk onto the central star. In models, this is generally assumed to decrease steadily with time, although some models do include a dependence with stellar mass. But they do fail to take into account one simple fact, that accretion onto the star is unlikely to be a steady process, because the disk cannot transport the material at the same rate that is being fed to by the envelope. For example, here, I show one of the models by Vorovyov et al. 2015, these fragmentation models. You see the changes in the accretion rate with time, and you can see this is highly episodic changes. So it doesn't decrease with time, but you see these highly variable accretion rates. And also, we have observational evidence that the accretion is not steady in young stellar objects, and we see these large changes in magnitude in these young stellar objects of up to 5 magnitudes. These are outbursts that can last up to 100 years. These are a few examples of the classical objects. And then theoretically, Harvard 2017 have shown that large, long-lasting accretion events can have effects on the final architecture of planetary systems, and they can lead to planetary systems similar to our own solar system. And observationally, we have seen this variable location of the snow line. This is a known young eruptive YSO, and CS et al. Have shown that the location of the snow line is at 42 AU because of this large outburst, when you would expect that generally the snow line to be located at 5 AU in a one solar mass star. Now, the problem with this outburst in young stellar objects is that it's not clear whether all objects go through these episodes of enhanced accretion. Also, the frequency and the amplitude of this outburst is not well constrained. Actually, there's only one observational study trying to determine this outburst rate by Scholz et al., where they compare Weiss and Spitzer photometry for young stellar objects. And they did determine an outburst rate, which is quite uncertain, between 5 and 100,000 years. And it's not clear that they only selected planet-forming YSOs or class 2 YSOs. They also include younger objects. It's actually biased towards younger objects. We also have some controversy as to whether these very large outbursts happen during the class 2 stage or during the planet-forming stage, or if they only happen at the earlier class 0, class 1 stages. Of course, if we want to determine this outburst rate, we could take one class YSO and monitor it for a long time, over 1 million years. But of course, nobody would give you money to do that. I did ask, and they said no. So what you need to do is to actually determine, is to maximize both the time baseline of your survey and the number of YSOs that you survey. So for the time baseline, this is where Gaia DR2 came in handy. We already have one all-sky survey, which is quite deep in the optical, which comes from the photographic plates. And we have the Supercosmos survey, which has digitized the entire collection, and where the first epochs are from the 1950s. And in here I show a really nice example from V2492 Cygnus. This is a known young eruptive YSO. You can see it's not there in the 1950s. It's somewhat brighter in the 1990s. And then in 2012, this is a Pan-STARRS image. It's is much brighter. Gaia is also an all-sky survey, and it can actually match the depth of these photographic plates. Here is the light curve of this object. I show 3 epochs, the 2 R bands, and this is Gaia, and this is an estimated R band magnitude from Gaia. And you can see that there is a large change of about 4 magnitudes. So we're trying to look for objects that show this kind of variability. And also, why do we use Gaia? Because it gives us a long time baseline. For this particular object, it's 61 years. So we have the time baseline, now we need the sample. So what we did was to take everything that could be associated with young stellar objects in SIMBAD. So premium sequence stars, T Tauri stars, Hervik AAV stars, emission line stars, anything that could be associated with star formation. And we classify this object by looking at their near and mid-infrared spectral energy distribution. We use different criteria, like the Koenig 2014 criteria using WISE colors, the slope of the spectral energy distribution between 2 and 20 microns, and also some near and near infrared colors. So everything here in blue is what we classified as class 2 YSOs. And we ended up with a sample of 15,000 of these objects, with a mean baseline of 55 years, which means that we effectively monitored 900,000 YSO years. The way that we tried to select these objects, we didn't make any direct correlation between Gaia and the supercosmos magnitude. What we basically did was to take, for a particular YSO, we took everything around in a 2 by 2 degrees box and compared Gaia versus, for example, here, this is a second epoch in our band. And you can see how these objects, which we assume are largely non-variable stars, behave. Then we take the magnitude of the YSO in Gaia, which is shown here in the black line. And so we expect that the object in the supercosmos magnitude to be located around here. So we basically analyzed objects around this narrow region around the magnitude of the YSO. And we, of course, if the object was found to be around here and now is here, then it means that it's a high amplitude object. But we did this comparison taking all of the supercosmos bands. For example, here is the comparison between G minus R1 and G minus R2. First epoch in R band is second epoch in R band. You can see that most objects in that 2 by 2 degree box locate here, while the high amplitude object, which is V2492 Cygnus in this case, locates here, well beyond the 5 sigma confidence limits. Okay, so we quantify the variability using the 4 by treating this G minus magnitude from supercosmos as a 4-dimensional multivariable normal distribution. We ended up with a lot of candidates, not because of Gaia. Gaia is a beautiful data set, but because, of course, supercosmos has some problems. For example, here the catalog shown as this object being not detected in R band and then really bright in Gaia, so we thought it was a high amplitude object, but however, it's a problem with the photographic plates. There's nothing there. There's also problems in high nebulousity areas. Supercosmos wouldn't detect an object here. You cannot see it, but it's quite there. At the end, we compare also with more recent surveys like Pan-STARRS and SkyMapper, and we ended up with 138 true variable stars. Now, 138 high amplitude objects represents about 0.9% of the variability of class 2 YSOs. So these are the most extreme variable class 2 YSOs. And this is a distribution of the amplitudes for these objects. Well, I'm not going to talk too much about this. Basically, it was to show that we are not complete below 2 magnitudes in amplitude, but we are complete towards a larger amplitudes that we are looking for these long-lasting accretion events. Now, what's the physical mechanism that drives this high amplitude variability? For objects in this region, for all of the objects, we try to add data from the more recent CCD-based surveys and try to classify the likers of these objects based on these available epochs. Most objects in this region shows what could be called irregular or recurrent variability because they sort of go up and down with this high amplitude. And here in this region, we find objects which can be related to hotspots or extinction-related variability. These are still interesting, and we are planning to monitor. We apply for time to monitor these objects. But for the case of this study, we're looking for these long-lasting outbursts, which locate preferentially in this region here. But again, we find a lot of objects here, but not every object in this region is an eruptive YSO. So we're also planning to monitor these objects to understand what's causing this high amplitude variability. For the case of long-lasting outbursts, we found 7 objects that we can classify as having this kind of variability. 4 of them already known, and 3 new objects, such as this one. In 1986, it was bright, but then it became about 4 magnitudes brighter in the R band. And this is kind of the likers that we are trying to look for, objects that were faint in supercosmos and then became really bright in Gaia. Given these numbers, we're able to estimate that the waiting time or recurrence time scales of the outburst is about 122,000 years. This is longer than the time that you would expect in the class 1 phase, as evidenced from the gaps between H2 nodes along the jets of YSOs. And we also reanalyzed a sample of Scholz et al. 2013 in order to only select class 1 objects. And we found there that we found a time scale between 3 to 20,000 years. Now, this means that in the class 2 phase, these outbursts are less frequent than during the embedded phase, but they still happen. So probably models of planet formation do need to take this fact into account. So thank you very much.
So time for a couple of questions.
Simon Hodgkin, Cambridge. How do you know you're seeing them now in outburst, as opposed to previously they were in a faint stage?
How do I know that they were before in faint state and now they're just...
No. How do you know that right now you've caught them actually in an outburst, rather than the previous early measurements weren't actually when they were unusually dim? Now they're just normal. What's the additional evidence that they're actually in an FU Orionis state?
For the ones that we found. For the 3 new that we found, we are applying to get a spectroscopic confirmation of this. But one of the new ones is actually quite interesting because we found the outburst, and in the literature it has some spectroscopic measurements. Some people think it's a giant star because of the spectra in the optical. But then it has also a spectra before the outburst that we have. And it shows the H alpha in emission. So it means that it actually changed from being a classical Titori star into this FU outburst. But yeah, we do need, for the other 2, we do need spectroscopic confirmation.